Team 112, TheHuzz, novel hardware fuzzing framework for detecting design level vulnerabilities. Members are Christian, Ian, and Anna Lee. So, introduction to TheHuzz. As the world continues to have these technological advancements, it has hardware design continually growing and becoming more and more complex. When we have hardware design, we need to have design verification that is able to detect security vulnerabilities at any scale, complex, non-complex, and everything. And fuzzing is an automated tool used for software vulnerability detection, which generates random test cases capturing bugs, crashes, and unwanted behavior. This works efficiently for large programs, and so this sounds very appealing for something like hardware design. Currently, whenever we implement fuzzing, it introduces several problems when applying it to hardware. This is where TheHuzz comes in. TheHuzz introduces a novel framework to address current challenges with implementing hardware fuzzing. So, the background of design verification. Basically, when manual writing of RTL design is written, this calls for design verification to address functional bugs due to human error, silly mistakes to ensure that specifications are met. This is done by testing with a test bench to see if the designs meet the specification. This is done at various and multiple stages for the design, and then the outputs are compared to a golden reference model to find any mismatches that indicate that there are bugs. The challenge with current hardware fuzzing approaches call for fuzzing the actual hardware RTL design.
So getting into the original methodology and how the HuzZ was tested, as a bit of background, the HuzZ works by fuzzing the hardware at the register transfer level using instructions as inputs, which are specified through coverage metrics that we've defined to target specific behavior. And so good coverage of the design is achieved through optimized input mutation. So if we find that certain area of the design space is interesting, then we kind of keep the same structure of the instructions, but just flip around some bits to get more coverage. And then the HuzZ was originally tested on 4 open source processors due to IP policy, those being Arion, Rocket Core, More 1KX, and OR 1200. And we used appropriate grain reference models for bug detection in order to potentially catch common weakness and vulnerabilities. So, also, these exploits for the bugs that were found were created to demonstrate their impact, and the HuzZ was compared with another fuzzer that performed similarly to fuzz RTL and 2 traditional verification methodologies used in industry today, those being formal verification and random regression. And here are the original results. We can see here that the HuzZ definitely outperforms random regression and the diffuzz RTL with increasing coverage and just more points covered with the same amount of instructions.
So how our team implemented the HuzZ is where we downloaded Boom v4 core on the Infamous Olympic servers, and we ran the HuzZ and random regression while also measuring the coverage it achieved. This is our results where you can see that about 650,000 coverage points was achieved for each one, where the random regression is actually slightly better coverage, and this was ran in 200 test cases. The limitations in our design where we could not replicate the results, and this can be explained by the boom core having more shallow coverage, where random instructions can quickly hit decode logic, issue queues, pipelines, and just more of the coverage points. And the HuzZ also has a warm-up cost to it, where it thrives in deep designs and also a large testing time. That is our presentation. Thank you.